We can give our speaker as much time as possible of Minecore, and I'll just say a very quick introduction about what this lecture series is before passing off to our host to introduce our speaker. This is the Benjamin and Anne A. Pinkel Endowed Lecture. If you just got on, this is now our 24th annual lecture. And this lecture fund was established through a generous gift from Sheila Pinkel on behalf of the estate of her parents, Benjamin and Anne A. Pinkel. And it serves as a memorial tribute to the lives of her parents. Benjamin Pinkel received his BSc in electrical engineering from the University of Pennsylvania in 1930 and was actively interested in the philosophy of mind and actually published a monograph on the subject entitled Consciousness, Matter, and Energy, The Emergence of Mind in Nature in 1992. The objective of the monograph was to re-examination of the mind-body problem in light of new scientific information. And this lecture series takes that as its theme and its inspiration. It's intended to advance the discussion and rigorous study of the deep questions that engaged Dr. Pinkel. So that's what the Pinkel Lecture is. It's always a highlight of our seminar year. And I'm going to pass the baton to Aaron Roth to introduce the Pinkel Lecture for this year.
Thanks. So as the token computer scientist on the Pinkel Lecture Committee, I thought hard about which speaker I wanted to propose, since this is an interdisciplinary event. And I wanted it to be someone who would represent the best of the field for those outside of it. And we couldn't have done better than our speaker, Cynthia Dwork. Cynthia embodies a fearlessness in her choice of research questions that I admire and aspire to. She tackles important questions that once seemed outside of the scope of theoretical computer science and brings new clarity and rigor to them. So Cynthia is currently the Gordon McKay Professor of Computer Science at Harvard, the Radcliffe Alumni Professor at the Radcliffe Institute for Advanced Science, and affiliated faculty at the Harvard Law School. She's also a distinguished scientist at Microsoft Research. She's a fellow of the American Academy of Arts and Sciences and of the ACM. She's a member of both the National Academy of Engineering and of Sciences and the American Philosophical Society. She's won the Gödel Prize, the Richard Hamming Medal, and the Knuth Prize. And she's one of the most visionary researchers in theoretical computer science. She invented proof of work in 1993, decades before Bitcoin, differential privacy in 2006, before the era of big data got into full swing, and made the first theoretical investigation into algorithmic fairness way back in 2010, well before it was a topic of public discussion. And I'm looking forward to her talk.
Thank you so much for the opportunity to be here, to give the Pinkel Lecture, and for that amazing introduction. It's a lot to live up to, and we'll see what we can do. Okay, so this is a picture of Barbara. Oh, wait, before I go on. I can't watch the chat or look for hands or things like that. If there are questions that are clarification questions, please put them into the chat and Aaron will interrupt me. And other questions, I'm going to ask that you hold until the end. But if there's something you don't understand, by all means, make sure that we fix that. Okay. All right. So this is Barbara Underwood. She is the Solicitor General for the state of New York. And in her clairvoyant 1979 article, Underwood discusses the use of individualized, or what was called clinical decision-making, and compares it to the use of statistical inference in what she describes as two different ways of approaching the task of moving from evidence to facts. And this dichotomy between individuals versus groups is one that we haven't gotten away from. And it's quite amazing to go back and read the kinds of things that Underwood said and to see how much she saw about the future and how very computer science-y some of her thinking actually is. Okay. So as Aaron mentioned, we started working on the theory of algorithmic fairness back in 2010. The first paper was published in 2012. And we identified at that time sort of these two flavors of definitions of fairness. That is, what is it that you might be wanting from an algorithm that is supposed to be fair? And the two flavors we called group fairness versus individual fairness. So there are many flavors of group fairness that have been posed in the literature following our work. We started with statistical parity. So the definition of statistical parity is, roughly speaking, that if we're looking at a classification scenario in which we classify some people positively and other people negatively, the requirement is that the demographics of the group that has a positive classification should be the same as the demographics of the population as a whole. And that would also follow for people who receive a negative classification. So for example, in the context of a college application, statistical parity would say that the demographics of the accepted students should be the same as in the population as a whole. A different notion that was posited later is, let's say, balance for the positive class. So that would be for a scoring function that assigns scores to individuals, which are roughly interpreted as the likelihood that this person is a positive instance. In the particular work that I'm thinking of, people are sort of born with a positive or a negative label, and you're trying to figure out which one they are, so you're assigning scores. So balance for the positive class would say that the average score that you assign to a positive member of a demographic group A should be the same as the average score for a positive member of demographic group B. Now, we felt that group notions fail under scrutiny. That is, we found them to be problematic. So here are some examples from our early work and also now commenting on later things. Let's suppose that you are advertising and, we think like cryptographers. And so our bad guys, we can ascribe as evil intentions as we want. So our bad guys could, for example, just be racist, or they could just, really not like people from one group versus people from a different group. And yet there may be some edict that requires them to advertise because they're working on a platform and the platform wants to ensure some kind of fairness. And the platform says, your ads have to go out they have to respect demographic parity across these groups. And now the advertiser is advertising for a steakhouse. And so what they do is they send steak ads to the people in group A because they like group A. I mean, to the meat eaters in group A because they like group A. And they send the ad for their steakhouse to the vegetarians in group B because they want to discourage members from group B from coming. So they are satisfying statistical parity in terms of the balance of ads to group A and to group B, but they're clearly only recruiting from group B. So what that says is that statistical parity is not by itself a good solution concept. And there are other situations that could arise. So the distributions within the groups A and B could be very different. And you could imagine a scenario in which you're recruiting from a minority people that are more assimilated or that look like the majority in some way. There's also this question of, well, which groups should we be considering when we're talking about group fairness? And what about the intersectional case, because clearly that's a very real scenario. This is a very, very important question. Both of these are very important questions, and we will return to them. It's also surprisingly hard to test for group fairness. In later works, for example, some works of like my host, Aaron, or my introducer, Aaron, there are actually some complexity theoretic problems with testing. But even for really, really basic versions of this problem with very, very few groups, a recent study in the Journal of Criminology of Neal and Winship show how benchmarking tests are very, very fraught. Then kind of the nail in the coffin that from our perspective, my perspective, is that there are many natural group fairness desiderata. And it turns out that unless you can predict perfectly, they can be mutually exclusive unless the base rates are the same in the various groups. So in one form of that result is due to Choldachova, another form of it is due to Kleinberg, Mullainathan, and Raghavan. So that's the group fairness scenario or situation. The alternative that we investigated is what we called individual fairness. The intuition for individual fairness is that, roughly speaking, people who are similar with respect to a given classification task should be treated similarly, or people who are similar with respect to a given scoring task should be scored similarly. And that's a pretty common and intuitive notion. And there is a strong legal foundation for it as well, that similarly situated people should be treated similarly. And the question of similarity clearly is very context or task dependent. So Aaron and I might be very, very similar for purposes of sending us recommendations on technical papers to read, but completely different when it comes to hair products. So the struggle in the individual fairness approach is to get some kind of understanding of who is similarly situated to whom. Even for a given classification or scoring task, we need some sort of a metric that says for each pair of individuals how similar or actually how dissimilar are they for this particular task. So there's this question of how do you find the metric? And so while it turns out you can do a lot if you have the metric, getting your hands on the metric or getting your hands on the right metric is surprisingly, I mean, maybe not surprisingly, but it's tough. And that kind of brought things to a halt in that direction for a number of years. Although there was some very, very interesting movement that started happening in 2018, and in particular in 2019, some lovely work by Cristina Ilvento talks about how you can learn a metric by interacting with a human arbiter who might have a very well-developed sense of how dissimilar individuals are for a given task, but may have trouble articulating that in a way that can sort of turn into a computer program. And so Ilvento kind of went a little bit into HCI land and noted that there are certain kinds of queries that humans find difficult. In particular, what is the distance between person A and person B? But others that people find much easier. Which among A and B are closer to C? That's an easier question. And so Ilvento did a lot of work building up, showing how to learn a metric by asking very few difficult queries to your human arbiter. And that more work has been done since then in that direction. So I won't go into the others, but some related things were done by Gillen, Jung-Roth, and Kearns, and also very interesting contributions by Kim Reingold and Rothblum, and by Rothblum and Yona. Rothblum and Yona in particular show, define a notion of probably approximately fair and correct as a generalization of probably approximately correct learning, and show how given metric information on a small subset of individuals, you can actually learn a metric that you can generalize metrics to unseen instances. Okay. So the real action over the last 5 years or so has been in what I'm going to loosely call the MultiX Framework. So I'm not sure how everybody got to this. There were two key papers that are mentioned here, but at least, you know, my feeling about this is that it was in part an attempt to bridge the group versus individual gap. So individual fairness is clearly a desirable goal, but it has its challenges in terms of the metric. Group fairness can often be easy to achieve, but it's not clear what it means. So the question is there something in between that is sort of doable, which is nice, and very meaningful? So this is where we're going to spend a lot of the time in today's talk. In the MultiX approach, what I'm calling the MultiX approach, we basically have some kind of a fairness requirement that is going to need to be to hold simultaneously with respect to all sets in some pre-specified collection C of sets. These are sets of people. And notice in my picture here, these sets are large and they're also arbitrarily intersecting. And then the X sort of specifies a specific kind of group fairness guarantee. So the idea is that you're going to have a kind of a group fairness guarantee or a requirement for how your scoring function or classifier is behaving on a group, and it has to hold for all of the groups in the collection simultaneously. I should mention that you know, stemming from this seminal work, both authors from both of these papers have been very, very prolific in extending and developing this line of work. And unfortunately, I won't have the time to cover their tremendous advances, but we will talk about some things. Okay. So, I've mentioned scoring functions, and I've alluded to the fact that they seem to refer to probabilities or likelihoods. So this brings us to the question of what are individual probabilities? So risk predictors assign probabilities to individual instances. For example, what's the probability that it will rain tomorrow? Or what is the probability that X, this person, will repay a loan? What is the probability that this tumor will metastasize under a given course of treatment? Or what is the probability that this individual Y will commit a violent crime in the next 2 years? So these are the kinds of things that people want to know. And the problem with it is that it's not at all clear what is the meaning of the probability of a non-repeatable event. So we can't sort of give X the loan, run history forward, see whether or not X repaid, rewind history, try it again, and then see in what fraction of these attempts X actually manages to repay. We can't do that. So what do we mean when we talk about a probability that X will repay the loan? So that's the problem that kind of occupied my head for quite a while. And I just want to comment about this, that without an answer to this question, we don't even know what we're looking for. Like, if we could write the ideal algorithm magically, what would be its properties? What would be the meanings of the numbers that the mythical ideal algorithm would actually assign? The question struggles to make sense. And since so much of artificial intelligence is in fact related to trying to do risk prediction, I would think of this as, pun intended, literally the defining problem of AI. Okay. So also, one thing that I realize is, coming from cryptography, we always assume probabilities. Like when we talk about events, well, we have our agents and we have the other agents in the world, and everybody is flipping coins, and our probability space is over the coin flips of all of these individuals. But that kind of thinking doesn't seem to actually apply in the kinds of scenarios that I'm discussing here. And so going into this a little bit, I realized that there's not even unanimity in terms of, or unanimous agreement as to whether probabilities exist, or maybe everything is completely determined and we just don't have the information or the computing ability to figure out what the answers are, what the truth is going to be, what truth is going to be revealed later. So even though throughout the talk, I'm going to talk about probabilities and even individual probabilities, and I'll say a little bit about what I have in mind about them, everything that I'm saying still will make sense in a world in which there are no probabilities and everybody is sort of either a 0 or a 1, but we just don't know what they are. Okay. All right. So let's just go into one example which has a moral to it, other than just probabilities. So in a lot of settings, the probabilities that you hear about when you go to the doctor, these are obtained from binary outcomes data. Like, yes, tumors that looked like this, that had the following treatment, you know, had a this % chance or a that % chance of metastasizing. So typically what that means is that, you know, there's been some kind of a study, and the study maybe looked at certain locations in the DNA, like here, the pink locations are the locations that were studied in study 1. And with this course of treatment in study 1, 70% metastasized. And my numbers are complete nonsense, of course. So, but there could be another study that looks at different locations in the DNA. And if we look at the locations there in that study, maybe 40% of the tumors metastasized with the given course of treatment. So clearly we don't know what to conclude about this tumor. And one of the reasons that I wanted to introduce this example is it shows you how crucial the representation of an instance to an algorithm is. So the representations are the locations that were considered like in the training data and that you then use for training your predictor. And so if you looked at different locations, you would get very different views of the world. And with this as a background, it's not very surprising that the choice of how individuals are represented to the algorithms, both in the training data and then later at test time, is a vector for bias, for the introduction of bias. So, you know, we just can't say this enough, that what you put into the representation matters enormously for fairness as well as accuracy. So with that in mind, we're emphasizing that in our discussions, X is the universe of all possible real people, but the algorithm is only operating on a representation of the person. It only knows what it's told about you. And so we picture that there is a representation mapping that takes us from our universe to, just getting a pointer here. It takes us from our universe X to representation space. And that's all the algorithm knows, is how the person is represented. Now, if the representation space is small, is not very, very expressive, then distinct individuals could be mapped to the same representation. But that's certainly not what we expect to be the case in general. And so in this talk, we're going to assume that the representations are rich, which means there will be no collisions, that for every element that we will look at in representation space, there will be a unique preimage. Okay, all right. So, yeah, good. So the representation mapping can obscure key information about that's essential for the task at hand. These are my collaborators in this work: Omer Reingold, Guy Rothblum, Michael Kim, and Galyona. And here I have them as instances. This is in X space. They're real, all of them. And they have their labels, 0, 1, 1, you know, whether these are positive, they have, right. So this is training data. When it's fed to, when it passes through the representation mapping, it may be that key portions of the individual are hidden, right? And this is labeled representations of instances. Now, here is my model. And when I say my model, I mean the one in my head. So in my model, there is a probability that is assigned to every individual in the universe by nature. Let's say at birth, it doesn't matter, by nature. And that the outcomes that are observed are drawn as from a Bernoulli distribution that has probability pi star of coming up 1 positive. So if you don't believe in non-integer probabilities, then pi star is just 0 or 1. And then the outcome, OI star, will be exactly that value, either 0 or 1, according to what pi star is. But if you think that there's nuance, then, or that nature has nuance, then you know, maybe pi star is 2/3, and then OI star is basically the result of a coin flip that has 2/3 probability of coming up heads. Now, since we think of representations that are very rich, and so there are no collisions in representation space, we can actually, you know, sort of transport pi star from I here in the universe over to the image of I here in representation space. So we can think of pi star as simply being attached to a representation of individual I. So what do we want from these probabilities? These pi, if we are trying to generate things that maybe mimic nature's probabilities, what is it that we want? When we say that we want our probabilities to sort of look like nature or look right, what could we possibly mean by this? This is, of course, a very old question and hardly new here. And it's been looked at a lot in the context of, say, forecasting. So every night the forecaster announces the probability of rain for the next day. And let's just assume that those probabilities are discretized, say 0, 0.1, 0.2, 0.3, and so on. So, so one condition is called calibration. And this is often viewed as kind of the least you could want from a forecasting system. And calibration just says that if we look at, for any possible output value V, if we look at all of the instances that the days for which the forecaster predicted V, then in fact, on a V fraction of those days, the outcomes are positive. So if we look at all of the days for which the forecaster said 70% chance of rain, then indeed on 70% of those days, it should have rained. And that's for all values of 70%. Now, it's well known that calibration doesn't imply accuracy. So calibration isn't everything you want. It's just one thing that you might want. And to see that calibration doesn't require accuracy, you know, a forecaster that just gives the kind of average, so it just gives the annual average of rain, like what fraction of the days does it rain per year. If that doesn't change very much year to year, then a forecaster that gives that prediction on every day will be calibrated. Not an interesting forecaster, not a very useful forecast, but it's calibrated. Okay. So there is an extensive literature on forecasting, and I just wanted to mention a few results. I had kind of attributed the study, the importance or the focus on calibration to Philip David. And so he doesn't think about it this way, but my way of saying his result, his 1982 result, is that nature's forecasts are calibrated with probability 1. And then Oakes in 1985 showed that no deterministic forecasting sequence can be calibrated against all sequences that nature could produce. And David then wrote a very interesting paper in 85 with connections to randomness, which you'll see why I really like as we progress in the talk. And argued convergence in the limit of predictions made by any pair of deterministic computable and what he called computably calibrated predictors, which, as he points out, suggests actually a notion of individual probability. So in some sense, I think that we are struggling with things that he thought about, a long time ago. Then Shervish said, you guys, you're all worried about calibration, but calibration by definition is a long-run criterion that may be meaningless in our lifetime, let alone even before the sun grows cold. Foster and Vora showed that randomization circumvents Oakes's problem. Then we will see perhaps something called multicalibration. You've seen the MultiX framework. Here, X is calibration, where the requirement is that the predictor will be calibrated on every set in a large collection of sets. And here they show this, that this can be achievable for even any collection of countably many sets. And then kind of the punchline of a lot of this line of work was by Sandroni, showing that forecasters, showed how to build forecasters that can pass any test that nature passes, although the forecaster has to know what the test is going to be. So very interesting line of work. All of that was for sequential forecasting, but a lot of these, like the notions that we're going to be thinking about will also make sense in the batch setting. So in the batch setting, it's your typical machine learning setting where you train on a training set and then you hope to generalize to test instances. And so the definition of calibration makes sense here too. If we build a predictor taking representations of individuals to numbers between 0 and 1, then if we look at what the predictor says for large classes of people, then again, what we want is that if we look at all of the people for whom the predictor said probability V of a positive outcome, then in fact, a V fraction of those should be positive. Good, so we have calibration and we've kind of established why we're interested in it. But now let's go back to fairness, because that's the theme of the talk. In this work, whenever there's a star, it always has to do with nature. Whenever there's a tilde, it's always an algorithm or something related to an algorithm that we built, that we, the algorithm designers, built, possibly with the assistance of training data. So suppose we have, these are predictors, and the predictors map representations to 0, 1. And Kleinberg, Mullainathan, and Raghavan sort of brought the notion of calibration forward as a fairness condition. So they said, look at a predictor and consider two disjoint demographic groups, A and B. Then fairness requires that your predictor should be calibrated on A and on B simultaneously. So if you look only at the people in A and the forecasts that are made only for the people in A, then those should be calibrated forecasts. Similarly, if you look only at the people in B and the forecasts made for them, those should be calibrated. So why is this a fairness notion? What they had in mind is that there would be no second guessing of the score. So a score of V will mean exactly the same thing, whether one is a member of A or one is a member of B. If V is 75% then it says, for the people in A who were assigned 75%, then in fact 75% of them will be positive, and similarly for the people in B. Now, here's an example of a predictor. The true labels give 1s to 3 people and 0s to 2. So the true probability of a 1 is 3/5. Now, this is calibrated because it's definitely the case that if we look at all of the people to whom the scoring function predictor P tilde assigned 3/5, then 3/5 of them are positive. On the other hand, if we look at these two demographic groups, the faculty in light purple and the non-faculty in dark purple, this predictor is not calibrated on either of those groups. So you can be calibrated on the whole, but not calibrated on the different demographic subgroups. And so fairness would say you should be calibrated on both simultaneously. So this was the introduction of calibration to the fairness literature, as far as I can tell. So I mentioned multi-calibration briefly before. Now that we have defined calibration carefully and we've seen some examples, a particularly fruitful direction has been multi-calibration, in which we require that the predictor should be calibrated simultaneously on a large collection of arbitrarily intersecting sets. Okay. Now, I said that the question of which sets is important. And I know I still believe this, but I was aware of the multi-calibration paper and it was very elegant and I liked it, but I really became interested in the kind of thinking behind it when I was trying to resolve the question of how do we decide which sets should be included in our collection of pre-specified sets. So in other words, we want to ensure some kind of fairness for demographic groups. How do we decide which demographic groups should we be considering? So my concern is that we are blinded by our ignorance and our ignorance as a society, and we don't necessarily know what sets we ought to be including here. And I had the great pleasure of being a Radcliffe Fellow, and that is a very interdisciplinary situation. And I was listening to a lecture about a religious thinker, a woman, and I don't even remember which century she was from, whether it was a 17th or an 18th century woman. And what she was very interested in theology, but women were not sort of permitted or certainly not encouraged to be theologists and theologians. And she wrote something very self-deprecating along the lines of, of course, my opinion on this doesn't matter. I can't really know about these things because I'm a woman. And I heard that and I thought, well, maybe she's just tongue-in-cheek and she's furious, or maybe she actually believes this. And so when we're thinking about how do we decide which sets should be in this pre-specified collection C, we have to start thinking about who's going to make this list. So if you just sort of think about advantaged and disadvantaged, the advantaged groups may not even be thinking about the disadvantaged groups and may not, in any case, be wanting to be helpful to the disadvantaged groups. The disadvantaged not only does it take a lot of energy to sort of fight for your rights and insist that you be collected, but you have to believe that your group ought to be included. And in the case of this religious thinker, it wasn't clear to me, did she actually believe that her group, women, my group, should be included? And I spoke to Mahzarin Banerjee, one of the inventors of the implicit bias test, about exactly this question, like, to what extent can we assume that groups that are oppressed have kind of adopted the beliefs of the oppressive groups? And she says, oh, absolutely, absolutely. So why am I belaboring this? Because in this paper, the authors suggested that the choice of sets be based on computational complexity. So for example, all sets that could be recognized by decision trees of height 6. And so if the information that we want for determining, or that ought to be included for determining sets, is kind of relatively easily computed from the descriptions, that would cover it. And so kind of complexity theory rocks, like it took care of the problem of specifying. This was my thinking at some point, and this kind of really woke me up. Now, in fact, the sets in multi-calibration play two different roles. One of them is demographic. One of them, we probably won't have time to go into it, but one of them has to do with kind of legitimately separating the sort of likely positive outcomes from less likely positive outcomes, because you want your scoring function to also be accurate. And another, I'm just sort of noting that the sets play these two roles. And I'm also noting, and we will return to this at the very end of the talk, that multi-calibration, it is in some sense not aspirational, in that is, it's trying to give a very clean picture of the world as it is. What is this person's chances of success? It's not moving us toward the world that we want it to be. So we'll return to that later. Okay. Great, so we've talked about fairness. That was one of the things in the title. Now I want to talk about randomness and pseudorandomness. So in a random sequence, there's no pattern. So the next bit is always unpredictable. In a pseudo-random sequence, which even the non-computer scientists would surely have heard of, in a pseudo-random sequence, the real definition says that there's no discernible pattern. In other words, there can be a pattern, but no efficient algorithm looking at the sequence of zeros and ones that was produced so far has any significant advantage at predicting the next bit in the sequence. So there's no efficient prediction method. And pseudo-random sequences are created by something called a pseudo-random generator that takes a short, truly random seed and kind of stretches it out with no additional randomness, so only by means of deterministic computations, to produce a longer output sequence that nonetheless has this unpredictability pattern where you can't predict the next bit. So, well, who can't predict the next bit? So the longer sequence has to look random, and complexity theory says, investigates heavily, looks random to whom? And here again, it's specified via complexity classes, just as our sets were going to be specified via complexity classes. So you might say that algorithms that run on a 1980s HP calculator in less than 24 hours shouldn't be able to predict the next bit. Or you might require that, or want to ensure that neural nets of 3 hidden layers and width 256 shouldn't be able to predict the next bit. Or decision trees of some fixed height shouldn't be able to predict the next bit. Or finally, what's done in computer science is you want to say that all polynomial algorithms will fail to predict the next bit. So that's pretty amazing. And in order to do something like this, you need what's called a complexity theoretic assumption. But if you've heard of the P versus NP problem, that's an example of a complexity theoretic assumptions, that there are things that can be verified efficiently that can't be computed efficiently. And so, yes, there are pseudorandom generators that work under certain complexity theoretic assumptions, and that produce sequences that look random to all polynomial time algorithms. Okay. So bringing this indistinguishability notion back to our problems, I want to talk about what we might want from our prediction algorithms. So one goal might be that the predictions that are made by our algorithm should somehow be indistinguishable from the predictions that are made by nature. Remember PI star, the hypothetical nature? So for example, so in order to formulate that, and we're going to formulate it in just the same way that theoretical computer scientists formulate indistinguishability for a pseudorandom sequence, we need a notion of a history. And a notion of a history is just a set of pairs, a prediction followed by the outcome for this person, a prediction followed by an outcome, and so on and so forth. And we need a notion of something called a distinguisher, which is also sometimes called a test, but I want to call it a distinguisher. And a distinguisher is a fancy name for something very simple. It takes a history as an input and it just says yes or no, 0, 1. So it makes a pronouncement. So here's how we can kind of summarize with a slight overstatement, the requirement of that long line of things that I was talking about earlier from the history of forecasting. I would call this, in my modern computer science language, prediction indistinguishability with respect to nature. So we think of two different experiments. The experiment on the left has histories that are made up of nature's predictions, that's the P stars, and nature's outcomes, those are the O stars. And here's a putative distinguisher, and it gets either a history of this flavor, or it gets a history of this flavor. This flavor has our algorithm's predictions, but paired with nature's outcomes. So P tilde is the algorithm's prediction, and O star is nature's outcomes. So the difference between these two experiments is whose predictions are being fed in. And prediction indistinguishability for a particular putative distinguisher D says, if we look at the probability that D outputs 1 when we draw a random history from this distribution, and we look at the probability that D says 1 when we draw a random history from this distribution, those two probabilities should be very close. That's all prediction indistinguishability with respect to nature means. So let's suppose then that we have a predictor P tilde, and we have training data, which is outcomes, and we have some distinguisher D. Can we test whether D actually is distinguishing nature's predictors from our algorithm's predictors? And the answer is no. We don't even know whether there exist non-integer probabilities. We don't have our hands on nature's predictions. The only thing we ever get to see are the outcomes that nature has assigned to people. So there's no way to test this. So even if we design an algorithm, we wouldn't have a way to test this. So we shifted to something which we call outcome indistinguishability. And it turns out that in the cases that are studied in the literature, if you satisfy outcome indistinguishability, then you will also satisfy everything that was desired in the previous stuff. So this is going to be a more demanding notion. So what is this new notion? Again, we have our two kinds of experiments. We have our distinguisher D, who's trying to tell the difference between one thing versus another thing. So that first one thing is our algorithm's predictions paired with nature's outcomes. We had that before. And now we have our algorithm's predictions, but this time paired with outcomes that are drawn according to the distribution, a Bernoulli distribution that has the algorithm's predictions as the parameter to the Bernoulli. So here we have nature's outcomes, and here we have outcomes that are made up according to our model of the world that's captured by P tilde. So the new requirement, outcome indistinguishability, says that we shouldn't be able to distinguish nature's predictions paired with true outcomes from sorry, I said the wrong thing. The algorithm's prediction paired with nature's outcomes versus the algorithm's predictions paired with outcomes drawn according to the algorithm's predictions. That's the new requirement. Now, outcome indistinguishability says exactly this, that for all distinguishers in a pre-specified large class of distinguishers, so you name your class of distinguishers and you say that given, do I have a picture here? No. Given the instance, the probability that the algorithm assigns to it, and what actually happens, that should look like the instance, the probability that the algorithm assigned to it, and outcomes drawn from that distribution. So why do we like this? There's a fantastic video of Feynman talking about how do you come up with a new law of physics? And he says, first, you guess the new law. That's where the physics comes in. You have some intuition, you guess your new law. And then he says, compute, you can kind of make this out. You compute the consequences of your guess. So if your new law is really a new law of physics, like a previously unarticulated law of physics, you should be able to compute the consequences of your law. What should you observe in the real world if your law is correct? And then you should compare this to experiments that you run to see whether the consequences of this law that you're guessing match reality. And he says, if they don't match reality, then your law is wrong. It doesn't matter how beautiful your law is or how elegant it is or how brilliant you had to be to come up with it. If the consequences don't match reality, it's wrong. And he says, in that sentence is the key to science. He also goes on to point out that if your consequences do match, your computed consequences do match your experiments, the only thing you know is that you haven't yet found out that it isn't a law, and you should compute more consequences. Now, from our view, we think of a predictor as a scientific theory. And let's imagine for a moment that the class of distinguishers that we want to consider is the collection of all polynomial size circuits. Then if polynomial size circuits cannot distinguish the world that we predict, that's this, from the real world, then the theory, which is embodied by the predictor, cannot feasibly be distinguished, period. Like there's no efficient method of distinguishing the predictions from your model of the world from nature's true model of the world. And so there would be no feasible way to falsify such a theory. Now you have to do a lot of imagining to get to this point that the class of distinguishers is the collection of all polynomial size circuits. And that's because you would need a very large sample size, too large for us to deal with. But I think this is sort of capturing what's exciting about this approach. Okay, so having come up with this and having viewed it in terms of indistinguishability, you can now actually come up with a hierarchy of demands that you wish to make from your predictor according to the amount of information that the distinguisher is given about the predictions. So at the base level, what we call no access outcome indistinguishability, the distinguisher isn't even told the predictions. It just either gets an instance of somebody in the universe together with the predicted outcome for them versus the instance together with what nature provided for them. Sample access is the version that we've been discussing, but there are more complicated notions where, for example, the distinguisher is allowed to say, well, yeah, you fed me some inputs and I see the predictions you've made on these inputs, but I'd like to see predictions of a few other examples. Like, I am now dreaming. Your inputs made me think of some possible scenarios, and I would like to know what does the algorithm do there. Okay, and that turns out to be a lot more powerful. So basically, there's a separation between the complexity of building predictors that satisfy these conditions and building predictors that satisfy these stronger notions. And I'm running low on time, so I'm not going to go into that, but I do want to comment that, well, two things. First of all, these two layers, low levels, are in fact provably equivalent to things that were studied in that work in which multicalibration was first defined. So those algorithms port over to this scenario. But I want to emphasize this gap between having oracle access to the algorithm and only being able to work with the samples that you're given. And that is the mathematical conclusion is that some kind of access to the predictor itself really matters. And the practical translation of that is that in scenarios where predictors are being used in real life, say, for example, to determine whether somebody is let out on bail or not, auditing the algorithm should permit, at the very least, being able to invoke the algorithm on instances of the auditor's choice. So California Prop 25, which was defeated, was a referendum on a law that replaced cash bail for certain kinds of charges with automated risk assessment, and it required annual fairness auditing. And the take-home message for that scenario of this work is that the auditing should allow some kind of access to the code, either to the algorithm, either at least through being able to ask questions of the auditor's choice or being able to actually investigate the code. Okay, I want to wrap up with one set of comments, which is that this line of work arose in the context of algorithmic fairness. And as I said earlier, this whole approach is descriptive. It's trying to get the best, most accurate view of the world the way it is, but it doesn't say how to fix the world and make it less unfair or how to reverse any effects of bias. And so in terms of trying to make the world better, you could say that the philosophy is to learn from the data about the real and unfair world, and then try to figure out what is the way that you should adjust in order to make things more fair going forward. So the way I think about it is this Q star is some hypothetical, wonderful world in which everybody is supported and really has all of the resources and lack of being beaten down that allows everyone to reach their full potential. And then there's some transformation, which takes us from this ideal world to the real world where people are oppressed and beaten down and discouraged and so on and so forth. And this transformation will destroy, in general, information. Like we can't work our way back in general. So it still is possible that we could imagine something that we could do that would improve things, that would, some kind of a tau that if we applied them to P star, we would get maybe a little bit closer to Q star, a little bit closer to understanding people's real capabilities. Now, we have samples from P star. That's like the real outcomes in the real world. So even though we can't see nature's predictions, we know what nature does. And we've seen that from that, we can build things that are indistinguishable from nature, indistinguishable to our collection of distinguishers. We have no samples from the ideal world. So the question is, under what conditions can we apply some transformation to a P tilde that we build and obtain something that has a desirable relationship to at least T of P star, if not Q star itself? And that's a line of ongoing work that is joined with Omer Reingold and Guy Rothblum. And I think I'd like to end here. So.
Thank you, Cynthia. So anyone in the audience who has questions, raise your Zoom hand, or if you prefer, type them in the chat and I'll ask them. Or if you want to go wild, just unmute and go for it. Maybe I'll start with one. So when I was, like, the first time I heard of these sort of calibration results from sort of the earlier economics literature that you mentioned, these sort of sequential forecasting results, my first reaction was, oh wow, like, these are super cool positive results. And then when I talked to Ricky, I realized that he, and I think many people in this literature, viewed them as depressing negative results, that there's sort of, since you can achieve all of these calibration notions, like, even without knowing what the distribution was, because you do it in this sort of sequential setting. And so there's sort of this feeling in this literature that this is sort of showing that there's no test out there that you can use to distinguish someone who really knows what they're doing from like a complete charlatan. So I'd be curious,
yes.
like, your view of this philosophical question.
Yes. So this is particularly worrisome somehow in the online setting.
Yeah.
Yes, indeed. We went back and forth and back and forth. But my view, so what was I going back and forth on? Charlatan, the charlatan can do it. But what's going on really is that the charlatan who begins as a charlatan is starting to learn.
Yep.
And so that would be the ray of hope for these sorts of things. And just about a month ago, I actually spoke to Ricky about this, and he concurred that, yeah, maybe that is a reasonable, positive way of looking at it, that the charlatan can learn. So, but I absolutely, I share the confusion about what do they actually mean. And I mean, there are things that it does not mean that we would like it to mean, but that doesn't mean that it's useless. It's useful.
Yeah.
And even though, for example, multi-calibration doesn't imply accuracy, if your algorithm is not multi-calibrated, you should fix it. There are simple post-processing steps where you could fix it and not hurt it, not destroy accuracy, only improve. So why not? And then I didn't mention, but there have been some interesting and useful applications of these techniques in medicine in two important settings that were written about by Rothblum and Yona together with collaborators from Clalit, which is the largest healthcare provider in Israel. One of them is a study which showed tremendous improvement for predictions of osteoporosis or maybe hip fractures or something along those lines. And another one was cardiac events. And the other was an early predictor for who was at most risk for severe illness or death from COVID, where they used information very, very early in the pandemic from China to calibrate a model that they had already built using copious medical records data about who is at severe risk from influenza. So, and as time went on, it turned out that their predictor was very good. But the influenza predictor by itself would not have been. Yeah.
Are there other questions from the audience? I know we're a little over time, but I think we've got time if anyone wants to. All right, well, maybe then let's thank Cynthia for giving us such a great talk.
Thank you for